and then introduce you. All right. Welcome everyone to the DDPS seminar. Before we introduce our invited speaker, let's go over some rules and logistics. First of all, please mute yourself during the talk unless you have questions. If you have questions, you are welcome to unmute and ask. Otherwise, please use chat room to post your questions so that we can address them in Q&A session at the end. Second, today's DDPS seminar is open to external audiences, so no classified discussion. And finally, the talk today will be recorded and uploaded in our YouTube channel. That's about it. Now let me introduce our speaker today. It is an honor to host Ying Liang, who is a Golub visiting assistant professor of mathematics at the Department of Mathematics of Purdue University. She earned her PhD degree in mathematics from the Chinese University of Hong Kong in 2021 under the supervision of Professor Jun Zhao. Her broad research area is in computational and applied mathematics. Her current research interests include ill-posed inverse problems, machine learning, numerical methods for partial differential equations, and scattering theory. Today, Ying will talk about data-assisted algorithms for inverse random source scattering problems. Please enjoy and accept a wonderful talk. Now, without further ado, let me pass the baton to Ying by asking one random question as usual. Today's random question is, where is your favorite place in the world?
Well, favorite place. If you don't specify the location, my favorite place, of course, will be home with my loved ones. As long as it's my loved ones, it's a home, then no matter where it is. But if you're mentioning a location, the city, then it might be Hong Kong at this moment.
Okay, Hong Kong. Hong Kong is a nice city. I've been there once. All right, stage is yours.
Let me share screen. Okay. First of all, thanks to you, Sue, for your kind invitation and introduction. So, as I just mentioned, I'm a second-year postdoc at Purdue University right now, and I'm very glad to be able to share with you our latest work on data-assisted algorithms for inverse random source problems. This is a joint work with Professor Liang Wang and Peijun Li, who I'm currently working with at Purdue. Now, I will start with a brief overview of what I will be talking about in the next 45 minutes. We are interested in the inverse random source problem. So generally speaking, it's an inverse problem. And for inverse problems, mathematically speaking, we try to determine the unknown coefficients in a partial differential equation via the exterior measurement. This could be explained with this diagram here. Now, if you're interested in a certain physical phenomenon, and it could be modeled by a partial differential equation, then the physical properties of that media will go into this partial differential equation as some coefficients in that equation. Now, if you have the equation, have the coefficients that you need, you can numerically solve it with finite element, finite volume, finite difference. And after solving it, you have the numerical solution to that equation. Now, the thing I just described is what we call direct problem. We simulate something solved for a solution. The corresponding inverse problem will be, you don't know about the physical properties, you don't know the information about the medium, but you have the exterior measurement of the quantity, which is the solution of the direct problem. And with this exterior measurement and our understanding of that partial differential equation, we trying to reconstruct that physical property of our interest. Now, this figure on the right-hand side is one device for solving the inverse problems. That's the electrical impedance tomography. It's a medical imaging type of problem. We attached current around the human body. We inject currents. We attach these electrodes, inject currents from these electrodes, and then we will measure the voltage induced by the current. And of course, this would be, we don't want to intrusive measurement in this case, right? So with the boundary measurement, we will be able to reconstruct the median coefficient inside the human body. This is governed by some elliptic equation. That's one concrete example of inverse problem. Now, the difficulty of solving inverse problem, there are several typical difficulties. The first one will be, it's possible that given the measurements of the solution that we collect, you cannot uniquely determine the physical property. And another thing is that it's possible that this inversion, this reconstruction is very unstable. If you have little noise, little perturbation on the measurement you collect, you will get very different reconstructed coefficient. That's not something we want because the noise in measurement are not avoidable. And also, it may require large-scale computations. You might need to compute some large-scale problems, or you need to repeatedly solving the direct problem to get a good reconstruction. And also, of course, uncertainties. Like you cannot say for sure that you have a accurate model, and you cannot make sure that you don't have uncertainty from the environment. These are the possible difficulties when solving an inverse problem. Now, when it comes to our problem, the inverse source problem, there exists some traditional methods to solve it that is purely based on the physical part, the understanding of the differential equations. If we want to reconstruct this target source distribution on the left-hand side, the reconstruction we get with the traditional method would be like this. It's actually an acceptable reconstruction because I need to emphasize that the measurement we have will be the just in the exterior, maybe on the surface of a certain domain. So it's not an easy problem, and this type of reconstruction is already quite well. You can tell that there are 3 obstacles. It's just that it's not very accurate. Also, traditional method works. There are several limitations, like it only works for certain cases, and I will explain when it works and when it won't work in the following sections. But it has several limitations, and of course, we want to have a more accurate reconstruction. That's when we consider, can we use some data-assisted approach to tackle these difficulties? And that's why we propose a 2-stage data-assisted method. For the first stage, we use some method inspired by the traditional ones. We use the physical information from the boundary measurement, we get some approximation of the coefficient. And in the second stage, now from the approximation to the exact coefficient, it becomes an image-to-image types problem. Now, this is a widely studied topic in computer vision, and that gives us that means we have different algorithms that we can try if that will improve the approximation. And we compare the performance of principal component analysis-based regression algorithm, U-Net-based regression, pix-to-pix, and the different type of neural networks. I will further explain these figures in the numerical experiments part, but is this just a comparison of the reconstruction using different types of data-assisted algorithms as the second stage. So physical-based numerical model is accurate and justified because we know that model, but they may not be available as we have some constraints that whether you can use the traditional method or not. And data can be appropriately incorporated to address these difficulties. And how to combine traditional methods and the data-driven method is an important research question. And machine learning techniques in computer vision are useful for imaging problems, especially for the image-to-image tasks. With these observations, we proposed our method, which successfully combine the physical information and the data we have. So now let's get started going to details about this, the words that I've mentioned. Now, the first question, what are the scattering problems? The inverse random source problem in the title is one of inverse scattering problem. Scattering problem concern the interaction between waves and medium. Wave propagation happens everywhere. We could be talking about acoustic waves, electromagnetic waves, elastic waves, etc. I'm talking now that I'm a source of some acoustic wave, and you see light everywhere. Light is electromagnetic wave. And the settings may like this. You have a point source axis here. It will induce some electric field denoted by E. When that electric field propagates, it could interact with something like this that will be obstacle. It may not penetrate this obstacle, so we need to add some boundary condition around it. And the wave will propagate and it will cross this interface S. And it might have different medium coefficients above S and below S. So the wave field will of course becomes different. And this process, like if we know about where is the source, know the obstacle, know the interface, then solving for the wave field E, that's the direct problem. And the corresponding inverse problem will be maybe we don't know where is that source, or maybe we don't know where is that obstacle, but we have the measurement of the wave field E around this plane gamma 1. Then we try to reconstruct to recover where is the source, or where is the obstacle, or the shape of this interface S. That will be inverse problem. Now, inverse scattering problem can be categorized into three types. The first class will be inverse medium problems. It's widely used for geophysical exploration, seismic imaging, ultrasound tomography, or biomedical imaging. If we are considering this type of applications, we have our gun here. This is like a point source that will be acoustic wave, and we can measure from the hydrophones here, measure the wave field. Then we want to so the wave propagate along all the three layers of mediums, and we want to recover the medium coefficients of this medium. That will tell us the properties of these mediums. Another type, inverse obstacle problems, used for radar and sonar, submarine detection, non-destructive testing, remote sensing, etc. This similar setting as the previous one, we still have a ship here. We still measure the wave field above the sea, and we want to recover the shape of the sea floor, that's sea floor tomography. Now, this time we're interested in that surface. And the last class will be inverse source problem. That is the type of problems we mainly focus on in this work. Inverse source problems are used for medical imaging, antenna design, and synthesis. These two figures illustrate the MEG tomography, which is another type of medical tomography problems. We have a device like this, and we will collect the electromagnetic field around the head. And when we recover the source that induced the electromagnetic field that we measured, we will know so where's the source, how that is distributed, will give the doctor the information to diagnose certain disease. Now, there is still one ingredient in the title that I haven't mentioned, that's randomness. We need to take randomness into consideration in the sense that inverse problems can involve uncertainties due to the unpredictability of the environment, incomplete knowledge of the system, random noise of the measurement, or fine-scale fluctuation in simulation. Like, again, as I'm talking, I'm the source of acoustic wave, but there are also air conditioner or refrigerator near me. They're also making they're also source, and they're the noise accompanied the source that we want to reconstruct. So the unpredictability of the environment needs to be considered, and it will go into the differential equation. Then it will become a stochastic differential equation. And here is a list of incomplete list of researchers who are working on the inverse problems involving randomness. And there are increasing interest in both theoretical and numerical studies of the random inverse problems. Now I really need to show some partial differential equations now. Inverse random source problems under our consideration is governed by this stochastic Helmholtz equation. So Helmholtz equation comes from the wave equation. It's a time harmonic form of the wave equation, and it's used to model the acoustic wave or electromagnetic waves in certain constraints. Now, for this equation, that U denotes the wave field that we can measure, wave field U, and this kappa denotes the wave number. It's a constant positive number related to the property of the wave field. This eta, it reflects the property of the inhomogeneous medium. It's a function with different value at different location. And right-hand side F is the source that induce such a field. We need to add this one line, which we call Sommerfeld radiation condition, to ensure that this direct problem has a unique solution. That is, if we know kappa, we know eta, we know F, solving for that wave field U is a well-posed problem. We need this Sommerfeld radiation condition. It basically tells us that when the wave field propagates far away from the origin, it will decay in a certain rate. Now, stochastic part comes from the source F. The source from F, we model it as a random function driven by an additive white noise. That is, F is equal to a deterministic function G plus a deterministic function H times the white noise. Here, G and H are two deterministic real value functions, and need to emphasize that if the right-hand side is only a deterministic function, then the problem is well studied. The direct problem is a common one. But if we add a white noise to it, all the previous theoretical results need to be checked again, because we don't even have a weak solution to this equation, and we only have the mild solution, but we can justify that it has a continuous modification. The related regularity results are shown in these two work. Now, corresponding inverse problem. If we have measurements of this radiated wave field U on the boundary of the ball with radius R at finite many wave numbers, we want to recover the statistic properties of the source. That is, we want to recover the average G and the variance H squared. Now, the problem, although this is looks like it's a simple equation, but there are different cases for the reconstruction related to this medium coefficient eta. We are not going to reconstruct this eta, but it will cause a difference when we do the reconstruction. If this eta equal to 0, that is homogeneous media under our consideration, it's a rather easy problem. And for the second case, this eta is not equal to 0, but we know the distribution of eta. Then this is a more difficult question to answer. Can we recover F? And for the third case, we know that eta is not equal to 0, but we don't know the distribution of eta. That is, we have unknown inhomogeneous media. Can we recover F? For these three cases, there exists previous method for some of them. For case 1, when we have homogeneous media, the way to tackle it is to formulate it as an integral equation and then use Kazma's method to reconstruct the source. For the second case, eta not equal to 0, but we know the distribution. We can solve an eigenvalue problem and then use Kazma's method to reconstruct it. For the third case, that's an open problem. Like we have eta, we don't know eta, we don't know source, and we don't know source. It's how to recover that source F without the information of the media. And that's where our method would work. Now, because as I mentioned, the traditional method for the case 1 will become the first stage of the method we proposed. So for the next section, I will give you a detailed explanation about how the traditional method works for the first case. Now, solution to that Helmholtz equation with the homogeneous medium have this type of solution formula. That solution could be represented with this integral of small g and capital G, and this integral between the white noise and the fundamental solution. G is a fundamental solution. In two-dimensional case, it will be a Hankel function. Next, we can take expectation and variance on both sides of this solution formula. And take the real part, we get the first line. Take the imaginary part, we get the second line. Take variance from both sides and deduct the imaginary part from the real part, we get the third line. Now, for these three equations, the thing I colored as blue will be where we can take measurement, right? This is a wave field. And the thing I colored red, they are the things we want to reconstruct. So all three equations can be represented as an operator equation. That AJ represented right-hand side, this integral operators, we have total information about the kernel of them. The reason why I need to do this deduction, this combination of the real part and the imaginary part of the variance, is that after we discretize this part, we get a better post AJ. It has singular value decays more slowly than with a single imaginary or single real part. Now forget about the PDE. Now we're just recovering this unknown G or H, which is a Q here, from the measurement of the boundary data with finite many different wave numbers, PJ. Recover Q from P. That's some linear algebra problems, right? Now we're gonna use the regularized block Cosmos method to solve it. And for the inner iteration, we do this type of update. And this could be illustrated with this diagram here. With initial gas Q0, we project it onto the solution plane corresponding to the first operator equation, integral operator equation, and then we project it to the second solution hyperplane, and to the third, do this iteratively. Eventually, it will converge to the solution we want. That's the regularized Cosmos method. Here we add this gamma as a regularization parameter, because this AJ star is still a quite yield conditioned matrix. Now, I've been talking about this traditional method. There are limitations to it. As I mentioned, recall that this PJ, what we call the measurement, comes from the left-hand side of these equations. We need to take expectation and variance of the measurement we collected. And this could be achieved by taking a lot of realizations and use the sample mean, right? That means there's no way that you can get a great approximation without a large number of realizations. Actually, more than 1,000 realizations are needed to reconstruct the average, and even more to achieve satisfying reconstruction of the variance. And here is some figure to illustrate this fact. This is the target we want to reconstruct, the source we want, and this is the reconstruction with 10 realization. This is with 100, this one with 1,000 realizations. And you can see that we have to use enough realization to get a satisfactory reconstruction. And secondly, the sequence QK we get from Cosmos method, it will converge to a minimum norm solution, which is quite blurry, as the one here. It's quite blurry. And moreover, for case 3, when you don't know the distribution of the medium, then you can't derive the integral equation at all. Here, this AJ comes from this right-hand side. This comes from the fundamental solution. we have to have information of the partial differential equation to write a fundamental solution. And when we have no information about the medium, this can't be derived. And we have some more theoretical results related to these limitations. If we use Cosmas method to find the limit of that QK and the error for each iteration between the iteration and the minimum norm solution we want can be decomposed into the noise error and iteration error. The iteration error will decay when you have more and more iterations, but the noise error, according to our analysis here, it will have an upper bound. And this upper bound is proportional to K, which means if you have noise in your measurement, this PJ, it will actually increasing when you do more and more iterations. And this coincides with our numerical results. Like if you use Cosmos, when you do more and more iteration, the measurement will, the noise in the measurement will deteriorate your reconstruction. So that's why you can't do a lot of iterations. So our observation will be like this. The thing I just mentioned, those physical-based numerical model is indeed accurate and justified, but they may not be available for certain cases, like if you don't have information about the medium. And also the data can be, but we know that data can be appropriately incorporated to address these difficulties. So now let's consider if machine learning techniques could help with this reconstruction. And the physical informations that we have could help us to give us a prior distribution of the data we used for the training in the second stage. Now, we talk about using neural network techniques for direct and inverse problems. A simple approach, a direct approach, would be taking the measurement as input, take the unknown parameter as output, train the neural network in the regression manner. And we know that this is not going to work very well. But as I mentioned, the measurement we collect are on the boundary of the survey of the domain, and the unknown distribution, unknown parameter y, is in the whole domain. It's like you're using the one-dimensional data to reconstruct a two-dimensional reconstruction. If you treat it as a black box, it's not likely that you can success in the reconstruction process. So there have been other attempts for the inverse scattering problems. Here we just list for, this is just an incomplete list. People try to combine the physical information and data in different ways. And I also need to mention that there are a number of methods to use the neural network to solve the forward problem, to solve the PDE. They are also useful tools for inverse problem, because traditional way to solve inverse problem will be casted into a minimization problems. And to solve the minimization problem, you need to repeatedly solve the direct problem. And this neural network related algorithm will accelerate this process. And also to learn that mapping is also kind of one of the operator learning process. So for a neural operator and some other algorithm also works pretty good for this type of problems. And our method is different from the previous mentioned ones in the sense that we use the physical information in the first stage and use the neural network, the image-to-image type of algorithm for the second stage. Now, in the first stage, we will use the thing we just mentioned, the Cosmas algorithm for the integral equation. Given that PJ, the measurement, we don't do a lot of iterations, okay? Because the more iteration you do, the larger the noise level, noise error will become. So we just do several iterations to get an approximation G0, H0. Now we get an image. So for the second stage, we learn the mapping between the approximation image G0 to the exact G approximated H0 to the exact H with the different method algorithms for the image-to-image type of problems. And we'll test these 4 different types of algorithms for the second stage. The first one will be the principal component analysis based regression algorithm. Second one be the compositional Kopman operator type. Third one be the UNet based regression algorithm. And the fourth one will be a pix-to-pix neural network. For the first 2 of them, we basically just first carry out the dimension reduction, and then we of the input and output space, and then apply linear regression. The difference in the sense that we use different way to do the dimension reduction. And you can imagine that the third and the fourth one related to neural network works much better than the previous 2 linear regression type. So I will mainly focus on the third and the fourth one, explain a little bit about how they actually works. Now, UNet-based regression could be explained with this diagram. UNet-based neural network would be an encoder-decoder architecture like this. Now, from here to here, from the measurement to the input image, that's where we use the Cosmos method for the integral equation. Once you get, after several iterations, you get an approximation image here. From this image to this image, there will be a contracting path and expansive paths. And for each block, we have this convolution plus convolution layer, batch normalization, and ReLU layer. The difference between this UNet and the traditional convolutional neural network will be we have this skip connection here. Therefore, we can preserve the features of the input image with these skip connections. The feature maps are passed to the corresponding layer in the expansive paths via these skip connections. And this is widely used method for the medical imaging to do the segmentation. For the training process, we will minimize this L1 error as a loss function. Now, the fourth algorithm will be the pix-to-pix algorithm. It's a conditional generative adversarial neural network. Could be illustrated with this diagram. For the GAN type of neural network, we need to train the generator and the discriminator, which are 2 neural networks jointly. The input of the generator will be the image, and output of the generator will be also image. Input of the discriminator will be a pair of image, and output will be a scalar between 0 and 1. And that jointly trained in the competitive manner, as the generator wants to generate the image resemble the target coefficient, and the discriminator will attempt to differentiate between the real pairs and the generated pairs. By real pairs, we mean the pairs coming from the training data, and generated pairs means that this X and the output of the generator, these pairs will be what we call fake pairs. This objective can be achieved by dealing with this loss function. This is a binary cross entropy type. The generator will be trained to minimize this one, and the discriminator trained to maximum this one. It's a conditional GAN. We need to add another term. This term is the loss terms for the generator, because we want the generator to ensemble to mimic the exact coefficient. Now, in the pix-to-pix algorithms, the generator's architecture will be, again, the UNet, and the patch GAN will be used as the discriminator. Now, finally, let's present some numerical experiments. For the training set, we have 2,000 samples, each with 3 cylinder inclusions, which are randomly sampled. The position, radius, and magnitude are randomly sampled. The measurement we have will be the synthetic data of 100 realizations of average reconstruction, and we need 1,000 realizations for variance reconstruction. This is already 1/10 of the realization needed for a satisfactory reconstruction for traditional method. And the measurement will be measured as 32 uniform distributed points on the circle. Now, the source will be, the sword of source will be within this square, and we have measurement along this circle at 32 points. And we have 5 wave numbers. Now, some numerical results. This is the average reconstruction in the homogeneous medium. From left to right, we have, that's the exact source that we want to reconstruct, the average of the source. Second column is the cosmos reconstruction, the thing we get from the first stage. Third column will be the PCA-based regression result. Fourth column will be the Koopman, the DMD type reconstruction, and this one from UNet, this column from the pix-to-pix algorithm. We can observe that from here, from the left to right, we get a more and more complicated model, but we get better and better reconstruction. We have a table here, like for the training time, PCA and Koopman, we need less time, and for UNet and pix-to-pix, we need 75 minutes, 75 seconds, and more than 10 minutes for the pix-to-pix. But the relative error decays in this manner. But we will see that pix-to-pix actually have a slightly larger relative error compared with UNet. But if you tell from the image, you'll see that it actually give us a sharper edge. Now, this is a variance reconstruction, the reconstruction of H square. This is a relative harder problem, and we have to find the same observation from the left to right. We get better and better reconstruction, and same observation here from the relative L1 error. Now, these are experiments for case 3. Recall that case 3 is when you don't know about the media, how to do the reconstruction of the source. And there are no existing traditional methods for it, but this is our reconstruction. The first 2 rows are about average reconstruction, and these 2 rows above the variance reconstruction. This is average, this is for variance. From the left to right, we still get better and better reconstruction. If you compare this figure with the previous figure, we will see that the cosmos reconstruction, the thing we get from the first stage, these are much worse than the previous ones because we don't actually know the exact model because we don't know the median. But the first stage is based on the fundamental solution of the homogeneous median. So but still, even with a much worse initial condition, with the help of this data-assisted algorithm, we get pretty good reconstructions. Now, this is a generalization test. Recall that for the training data set, we use the 3 inclusions type, the cylinder inclusions. And if we test our result for the, like here we have 5 cylinder inclusions, and from this row, we have the simplified phantom type. We have ellipse inside, ellipse-shaped inclusions. We still get pretty good reconstructions. Okay, and here I conclude with some ongoing and future work. As I mentioned, there are all different types of scattering problems, and the inverse source problem we just mentioned is actually a linear type. And here we consider the inverse off-circle problems. That is, this is the differential equation under consideration. We want to recover the shape of this B. And this is a clearly nonlinear problem. And this is the reconstruction we have. We also use some traditional method, not integral equation, but some direct probing type. With the measurements we collect, we could get this type of reconstruction from the traditional method. Then we learn the mapping from this one to the exact coefficient, and this is the reconstruction we can get with the same amount of training data. And you can see that there are barely difference between the exact off-circle distribution and the reconstruction we get. And some other ongoing work will be the theoretical analysis for the stability estimate for this type of inverse random source problems which are of great theoretical interest. And here are some references for the works that I have just mentioned. Okay, then that's all I need to talk about. Thanks for being here.
Okay, thank you so much for the wonderful talking. Very nice results. Very impressive results. All right, so let's have a Q&A sessions. Anyone who has a questions, you can unmute yourself and then ask questions. I guess while you're preparing your questions, I can ask question here. So if you go back to slide 28, I believe, so there's a the comparison of the results, among 4 different the data-driven approach, data-assisted approach. Here, you said the time of the unit is 74 and the peaks to peaks is 729. That's the training time.
Yeah, that's for training.
And when you do the training, I assume you use a lot of, data.
Yeah.
In supervised manner.
Yeah.
And once you're done with the training, actual this predictions or evaluation of that the source locations or the source terms, it's very fast, right?
Yeah, testing takes no time. Like for the first stage, yes, you still need to do the Cosmos, but it takes not comparable to the training time. And for the second stage, you already get the trained neural network, so it takes no time.
Yeah, so I mean, looks like there's an offline and online stage.
Yeah.
Where you can collect the data from that physics-based inverse problem.
Yeah.
And you match those with a known the source terms. And that you train the unit and peaks to peaks. And once that is done, you can try that on to new source terms. But because there's a 2 stages, the first stage you still have to solve inverse problem in traditional way, right?
Yeah.
So that takes time.
Yeah, that takes a little time because it's a solving. So basically, we just solve this equation, right? And we solve it with Cosmos. If we only do several iterations, then this thing takes no time because this A is not really that large.
A is not that large.
Yeah.
How does the size of the A determines?
Now, so for example, here we have here we got some 64 times 64 pixels. So the input of this matrix A will be this Q that's from the unknown G or H. So it will have 64 times 64 as the one side of the matrix. And for another part, that will be PJ, that's a boundary measurement. So that will be 64 times 4, 1. Okay. And actually, that's from the boundary measurement. We use 32 measured points. So that's actually just 32.
Okay. And the A matrix here is dense matrix.
It will be with these types of kernels. So yes, it's a dense matrix.
Yeah. So if the pixel size is bigger, the dense matrix becomes bigger. Yeah, I guess as long as we deal with the 2-dimensional image, I guess we can handle that.
Yeah. Another difficulty also lies in the preparing for the data. Like for each sample, we need 100 or 1,000 realizations. For each realization, you need to solve the forward problem once. So for each sample, you need to solve it 1,000 times.
Yeah. Yeah.
So
Yeah.
that's a problem. Yeah.
Yeah. Well, that's the problem of any data-driven approach. Generating data is not an easy task. All right, sounds good. Is there any questions from audience? Well, if not, I have one more question. So if you can clarify, how you apply the Kuhlmann type data-assisted methods. So PCA, it's clear to me you do some sort of SVD.
Yeah, I see. So for PCA, yeah, we just grab them as vectors and concatenate the two matrix. Yeah, for PCA, we just do it separately. We do the SVD decomposition for the input image listed once and listed as a whole matrix, and we separately do SVD for the output image once. And we need to use that use sigma weight decomposition with the new the redacted dimension redacted new A will be you transpose the data and V and the sigma inverse from that from the different
that is
decomposition of the input and
somewhat,
output.
Yeah, that is somewhat clear to me. But the Kuhlmann type.
Oh yeah.
How did you come up with some linear operator, right?
Yeah, that's one thing. That's why I have a little bit doubt about how to say it and name of this algorithm we do. So we don't actually have the dynamic system.
Yeah.
Right. It's just a one-step dynamic system from like here to here. So we just see it as a one-step dynamic system. And
got it. Okay, and then you have a bunch of different the previous step and then next step, and you just pair them and then come up with the approximate linear operator. That's what you do for the Kuhlmann operator. Okay, got it. Okay. Have you tried completely getting rid of the physics, the first stage?
Yeah, that will be very hard. That will be very hard to train. Like to start with, if you don't use the first stage, what you have is I don't have the figure showing the solution, but if you have this type of source, the solution will be the oscillating, the wave distribution, and what you have is only so there will be a circle, we measured around the circle. It will be just a curve. Even if you have 5 curves, because we will have 5 real numbers, it's hard to get from the curve to the whole integral distribution. It's the dimension does not match.
I see. All right. Okay. We have a question from Petro. Do you want to unmute and ask?
Yes, actually, the first stage when you do iterative solution, how do you select stopping criteria? How to decide when to stop iterations?
Yeah, that's a great question. It's hard to decide because we have some theoretical result here that because the noise comes from the measurement noise, and also the error of the p comes from the mean sample mean, so it's unavoidable. So it will increase, the noise will increase. So it's hard to decide. So eventually we decide just to do 5 iterations and stop. And that's why you don't have a very good reconstruction here. But it's not guaranteed that you do more iteration, you will get a better one. It might get even worse reconstruction, so we just decide to do only several steps. Once you get a reasonable initial approximation, we stop.
Could you please show that slide with lemma?
Can you say that again?
Could you please show the slide when you which bounds your error reconstruct? No. Previous. Somewhere at the beginning.
Okay.
At the beginning, yeah. You showed it just recently when I asked you about
Yeah,
stopping criteria.
slide 15 or something.
Yeah, probably.
Something like that. Yeah, in the middle.
From here.
Where as the iteration goes up, the error is increasing.
Okay. Yeah, isn't that here?
Yeah, that one.
Yeah.
So help me to understand. We have two sigma gamma here. Which is which?
Yeah. This sigma gamma is related. It's the smallest non-zero singular value of this operator comes from the so it's all these metrics are related to something about the kernel here. And here, that delta gamma, this one is proportional to the L2 arrow. So this one is fixed. We know that it exists.
Now let me understand system of equations. So Pj is your data, right?
Pj comes from our measurement data. Yes.
Yeah. So Pj is just one data point. It's a scalar, right?
Pj. Pj comes from here. It's a vector. After discretized, it's a vector, like 32 by 1 vector.
Okay, so it's a vector at one position. Okay, and Q is your image, right?
U is U is our Q is the image that we want.
So basically, Aj is your operator, like a three-dimensional operator which maps two-dimensional image to one-dimensional vector, right?
Yeah, correct.
Okay, thank you. Thank you very much. Very interesting.
Thank you.
I agree. It's a very interesting work. Any other question? Well, if not, let's thank our speaker, Ying, for the wonderful talk. Yeah, thank you so much, Ying.
Thank you.
And after this talk, hopefully, fruitful collaborations will set up. And yeah, let's hope for that.
Thank you.
Okay. Thank you, Ying. And thank you, everyone.